So to follow up from the cross-sectional volumes, we have volumes of revolution. This is 6.2 again, but part 2. And this is the disc or washer method. So if I have a volume of revolution, that means I have some kind of a solid whose side or contour is described using some function, and I spin that function around some axis and I get an outline of this solid. And with calculus, I'm able to determine the volume of the solid by studying basically the outline of an object. So for example, let's consider sine of x, and we'll revolve it around the x-axis. So I'm looking at sine of x from 0 to pi, and I want to revolve this around the x-axis. And when I do that, I'm going to have basically an upper side and a lower side, but it's going to be spun around, so it's going to be round. So I can tell kind of right off the bat that I have cross sections perpendicular to the x-axis, which are going to be circles. So according to the last section, this is a cross-sectional volume, and so I would have to be integrating from 0 up to pi the area of the cross-sections. So since the cross-sections are circles, well, I'm looking for what is the radius of this circle, or later on, further down the line, I might have a slightly smaller circle, but the radius at x is going to be sine of x, or the function height. So the area of the cross section at x is going to be pi times the radius, which is sine of x, quantity squared. Or in terms of my integral, I'll be integrating from 0 up to pi times sine of x squared dx. But if I want to evaluate this integral, well, I'd have to evaluate the integral of sine squared of x, but we know how to do that from section 7.2. And to do that, I would have to use one of those half-angle identities. So this is 0 to pi. Sine squared of x, that becomes 1 minus cosine of 2x over 2. So I have pi over 2 out here, and a 1 minus cosine of 2x in here. So if you allow me to skip the u substitution on that second part, I should end up with x minus sine of x over, sine of 2x over 2, evaluated from 0 to pi, which means I have pi here, minus sine of 2 pi is 0, and if I plug in 0 to these, I'm going to get 0 for both. So it looks like my volume is pi squared over 2. And these volumes of revolution kind of generalize. If I have any kind of curve and I want to revolve around the x-axis, then I'm going to get a mirror on the other side. So the volume of revolution using disks, because the cross sections or the slices of my object are all going to be circles, is v equals the integral, well, pi times the integral from from a to b of the square of the function dx, because each slice is a circle and the radius of that circle goes from the axis of revolution, which is the x-axis, up to the function. So these heights, or these radii, are all function values. And the area of each slice is pi times the radius squared. So what if I want to revolve around something other than the x-axis? Let's suppose I've got the square root of x. And I'll go from 0 up to 4. But I want to revolve around y equals 5. That's parallel to the x-axis, but it's a little bit different. So I want to find the volume obtained by revolving y equals the square root of x on 0 to 4 about the line y equals 5. But if I do that, well, the distance from the axis to the curve is here. So what I actually end up drawing is some shape spinning around y equals 5 here. So I'm dealing with all of this stuff in here instead of something going around the x-axis. So I have a solid here, but what is the radius that I'm dealing with here? I know I'm going to have pi times the integral times some radius squared, but I'm going to go from 0 to 4. But the distance from the axis to the curve is actually 5 minus the square root of x. And to solve that, I would just multiply everything out and apply the power rule everywhere. But let's suppose that I wanted to use the same region as I would use revolving around the x-axis, but I want to revolve that around y equals 5. I would have to completely rephrase the question, because I need to specify the region that I want instead of just simply trying to use a curve, because the curve, just using the curve, it gave me the area up here, which might not be what I'm after. So let's try this again. But this time, I want to specifically use this region, and if I revolve that region around, I'm going to end up with a hollow solid. It'll look kind of like a misshapen donut. So I want to find the volume obtained by revolving the region bounded by y equal to the square root of x equals 4, and the x-axis about the line y equals 5. So I've already drawn the region here. Here's the square root of x. Here's x equals 4 as a vertical line, and the x-axis is already there. So a little more about what this looks like. I want this region revolved around the line y equals 5, I end up with getting something a little like this. Where I have kind of an annulus. So each of my cross sections look like hollow rings. And how do I deal with the area of those hollow rings? Well, I take the area of the bigger one and subtract the area of the smaller one. So I'm going to need to know the inner radius and the outer radius. So I would like to use pi r squared, but what I'm going to do is I'm going to find the volume of the whole solid with the far radius, and then I'm going to subtract the volume of the inner solid with the inner radius. Now the outside one, if I imagine, looks like a giant cylinder, but the inside one looks a lot like the volume I just wrote an integral for in the previous example. So I know I'm going to have an integral. I know I'm going to have a pi. I know I'm going to have a 0 to 4. But this outside radius is y equals 0 away from 5. So I actually have a distance of 5 minus 0. That's for every slice. So that's a big circle. Minus the smaller circle with the inner radius, which is 5 minus the square root of x squared. And again, to evaluate this, all I really need to do is multiply everything out, and I'll just need to use the power rule for this problem. So this lets me write a slightly more general formula, which is washer method. Let's say I have an axis of revolution, which is c. I've got one function, f of x. I have another function, g of x. And I want the area between the two revolved around the axis c. Then what I have to do is I have to find out what the outside radius is. I have to find out what the inside radius is. And I always have to work. It's important to work away from the axis of revolution. So I always start the line there and find out how far I go to get to the radius. So I've got pi times the integral from a to b, whatever those are, and now with the inside radius, and now with the outside radius, minus the inside radius. So the difference between the two functions doesn't happen inside of the square, it happens on the outside of the square. You can have one squared minus the other squared, because it represents finding a very large volume and then subtracting a volume out from the inside of it. So in terms of this particular picture, I would have the integral from a to b. The outside is g of x. Well, c minus g of x squared minus c minus f of x squared. So this is the volume. I'll say that this integral represents volumes from washers of a region revolved around the line y equals c. Now the important thing about washers is that the axis of revolution is parallel to the axis of integration. So if I want to revolve around the line y equals 7, well, the line y equals 7 is parallel to the x-axis, which means my integral must be in terms of dx. But if I want to revolve around the y-axis, then I'm actually going to have to use an integral, which is dy. So if I wanted to find the volume of revolution of the square root of x from 0 up to 4, but I want to revolve around the line x equals 0, or the y-axis, I would have to do something different. So I want to find the volume obtained when the region R is revolved around the y-axis, and this region R is the same as it was before. R is bounded by y equals the square root of x, y equals 0, that's the x-axis, and x equals 4, that's that vertical line over there. So what I'll have to do is I'm going to have to look at this sideways, and I'm going to have to solve everything in terms of y, because my integral has to be in terms of y, because my axis of integration is the y-axis. So I need to be making my slices in this direction instead. So if I'm making my slices in that direction, it means I'm going to have an inner radius and an outer radius, it looks like, where the outer radius is x equals 4, and the inner radius is whatever this curve is in terms of x. So my function, f of x, was square root of x, so I'm going to have to translate that into a function of y. So if y is equal to the square root of x, and I solve for x, that means I'll have y squared equals x, which I could call g of y. And using washers on that, I would have to integrate from 0 up to a y bound. Well, when x is equal to 4, that's when y is equal to positive or negative 2, but I'm dealing with the positive case here, so I'll end up here with a 2, and this is dy. But my formula stays the same. It'll just be in terms of y, so I have pi times, I have an outer radius of x equals 4 squared, minus an inner radius of x equals y squared squared. So I have pi times the integral from 0 to 2 of 16 minus y to the 4th dy. And that's what I'd have to do if I wanted to revolve parallel to the y-axis. But there are some functions which are potentially impossible to solve for y, and others which are just simply inconvenient. For example, what would I need to do to revolve, let's ask it this way, what about the first example actually? Sine of x. Suppose I wanted to revolve the area under sine of x from 0 to pi around the y-axis. That's not so easy to deal with in terms of inverse functions, and so I'm going to have a different technique in order to handle that. And we're going to do that in the next video, which is about, it's the shell method, which is a method of calculating volumes not based on slices, circular slices, but this time with kind of like soup can labels.